Righty, so let's get stuck into trig. So the trig definitions for us is our SOHCAHTOA type thing. So we have our sine, our cos, and our tan, and the acronym is SOHCAHTOA. So that's how we can remember it. And if you can remember this triangle, it's really helpful because when we talk about exact angles later on, it means that you don't have to do pure memorization and you can actually use these properties to help you find whatever the angle you need to find. And that means that you don't really need to memorize the table, but you can do that if you'd like to. So it's SOHCAHTOA, so sine is opposite over hypotenuse. We have cos, which is adjacent over hypotenuse, and then we have tan, which is our opposite over our adjacent. And the main thing to recognize is because of the relationship between sine and cos, if we were to place this angle here, so as long as this is a right angle triangle, if we were to place this angle here compared to here, the values would be the exact same, but they would just swap for sine and cos because we're just essentially swapping which side's adjacent and which side's opposite. And with the tan, we'll just get 1 over that value. Cool. So let's talk a little bit about our unit circle and what that is. So our unit circle, like the name suggests, it's a unit of 1. So it's a circle that goes from 1, -1, 1, -1, right? And that's how our kind of unit circle is going to be measured. So the most important thing is that the positive angle is measured anti-clockwise, so it goes this way, whereas the negative angle is measured clockwise. I'm not sure why that keeps on coming up. So essentially the main thing to remember is that it's always anti-clockwise from the positive x-axis, so that's something that you can make sure to remember. And another thing is that if you want to measure negative angles, you can go in the opposite direction. Alternatively, there's another way to write it where you can kind of go all the way around and then you can write it that way as well. So we talk about angles generally between 0 and 360 degrees, or alternatively 0 to 2 pi, but you'll see when you go through methods or special or whatever, essentially you talk about angles in any cycle and you can have multiple cycles to get to the same angle and you'll get the same result. So as long as you know, if you're going all the way around, then you end up in the same place that it was before. That's totally fine. You'll just get the same value for it. So what's an important thing also to remember is that with the different quadrants, different things are positive or negative in different quadrants, right? So there's a couple of different ways to remember this, and you can really use whichever method you think works the best for you. But I used CAST, so C-A-S-T. Another thing you can also recognize, which means that you don't have to remember an acronym, is that with our -1, 1, -1, remember it's literally just a circle, and we know which side is the positive direction of the x-axis, and we know which side is the negative direction of the x-axis, right? And similarly, we would know which one is the positive y-axis and which side is the negative y-axis. So using that knowledge, we can actually try and figure out which side is positive and which side is negative. So evidently this is not as helpful with tan because tan doesn't have a direct equivalent, but for sine and cos, because what we can do is essentially the cos component will just be this component here, right? And then the sine component will be the component up here. So because our sine is always our vertical and our cos is always our horizontal, essentially what we can say is when we're on the positive direction of the x-axis, we can say cos is going to be positive all on this side of the graph and cos is negative on this side of the graph because it's the negative side of the x-axis. And generally that does correspond. And so if we look here now and we're thinking sine, we can see sine is going to be positive up here and negative down here. So that's kind of how it works, and that's a way to remember it as well. You can come up with essentially any acronym you like. I think CAST works well, and as long as you remember what each of them are. So in this quadrant, cos is the only one that's positive. In this one, all of them are positive. In this one, you have your sine being positive, and this one you have your tan being positive. And that's essentially because your cos and your sine are both negative, and your cos and your sine are both positive here. So those two quadrants it's positive in. So essentially in every rotation going like this, there's going to be every 2 pi, there's going to be 2 quadrants where sine is positive, 2 quadrants where cos is positive, and etc. Cool. Alright. So let's talk a little bit about the exact angles, and you'll need to know this both for spec and for methods, so it's something quite important for you to know overall. So there's a couple of different ways to actually memorize this, and it's really up to you which way you do want to memorize it, but the key thing here is that you pick a way and then you just kind of know. So there's kind of 3 ways that people talk about. So the first way is going to be talking about this table method right here. The second method is going to be talking about your triangles, and your third method is going to be talking about your hand method. Alright, so we'll go through these 2 today. With the hand method, look it up on YouTube. It is quite interesting how they do it, but essentially it's based on the 5 fingers, and you kind of base it on which angle. So you choose one side to be one angle, and you choose one side to be cos and one side to be tan and all that kind of stuff. And then from that choice, essentially that leads you to be able to recognize which one, kind of from your fingers, counting over your fingers. It allows you to recognize like whether it's like root 2, root 3 or root 1, and you kind of can figure it out from there. So that's kind of a good way to memorize it, especially if you're comfortable with using that method and you can memorize it quite well, and you know you like that method quite well. Personally, I'm a little bit biased, I guess, because I really like the triangle method quite a lot, because I think it's quite handy and quite easy to do, and it requires the least memorization. But the table method definitely is also quite useful, especially if you have a lot of angles that you need to figure out that you can't really be bothered with just doing each individual triangle for and having a look into that. So essentially with the sine, cos, tan ones, what you want to do is you want to make sure you recognize when sine is 0 and when sine is 1, right? So if we look in our unit circle and we look where sine is, so sine is our vertical, we can recognize that when we get to pi on 2, which is 1/4 of that circle, we're going to get to that is going to be 1, and this part's going to be 0. So working the other way around, we can recognize that cos is going to be 0 here, right? And sine is just going to be, cos is going to be 0 here, and then sine is going to be, cos is going to be 1 here, and cos is going to be 1 here, and cos is going to be 0 here, right? So we'll have 1 and 0. So you've got your equivalent so far. Now, the way to do this is essentially you just count upwards. So you go root 1, root 2, root 3. And all of these are all going to be on 0. All going to be on 2. So 2, 2, 2. So what that actually gives you is root 2 on 2. You can either simplify that to 1 on root 2 or leave it, but you can definitely simplify the 1 out, right? So it'll just be a half in that section there. And then you just do it in the opposite direction for this one. So you essentially, it's just going to be root 3, root 2, and root 1, which is just 1, all over 2. And that's how you can memorize those angles. Another way you can also do it is if you look at the on the sides as well, if you want to memorize which direction it goes in. So as long as you have your angles in ascending order, and you can just remember sine is ascending and cos is descending. So you go root 0, root 1, root 2, root 3, root 4. And root 4 is just 2, so 2 on 2 is 1, so that's how it works out. And then you can go root 4, root 3, root 2, root 1, and then root 0, right? So then with tan, what you do is, because tan is just sine over cos, so essentially you pretend to divide over a line. So 1 over 0 is just going to be 0. 1 over root 3 is going to just be 1 over root 3, or root 3 on 3. Then root 2 on root 2 is just going to be 1. And root 3 on 1 is going to be root 3, and 1 on 0 is going to be undefined, and this is where our asymptotes occur for tan. So that's how you can memorize it. Another way to do this is using the triangles, which essentially you have 2 triangles. You have one triangle which is your pi on 3, pi on 3, pi on 3, and you have one triangle which is your pi and 4 triangle, right? So what you do is, this is an equilateral triangle, and what you do is you kind of cut it in half, right? So because we're cutting it in half, the easiest thing to do is just use 2, but if you wanted to, you could use any number you really wanted to. For our purposes, 2 is probably the easiest, but you can make up a number if you don't remember it. So we can go with 2, and then we chop it in half, so this becomes 1, and then using Pythag we can figure out this is root 3. So now you've got this angle on here, which is going to be your pi and 6 angle, so i.e. half of your pi and 3, and this one's still going to remain your pi and 3 angle. And then from there you can essentially just use SOHCAHTOA to figure that out. And then with this other triangle here, it's going to be an isosceles right angle triangle, so we can just use 1, 1, and using Pythag we can figure out that's going to be root 2. And so what we'll get here is this is just going to be pi and 4, i.e. 45 degrees, and you can figure out all the other stuff from there as well. Cool. Amazing. Alright, so there's a couple of things that they talk about, like I guess the complementary and the supplementary angle rules. So the main thing with these ones is you don't have to memorize these, because these ones are less, like you can kind of figure them out by using the unit circle and figuring out which quadrant it sits in. That's because essentially, you know, your pi minus x and your pi plus x, that's just going to be up here or down here, so you can kind of figure it out from there. So these are essentially just saying what they're equivalent to, because these are, so if you imagine this is in the 4th quadrant, this is in the 2nd quadrant, and this is in the 3rd quadrant, which we talked about how using the CAST acronym, that tan was positive in 3rd, sine was positive in 2nd, and cos was positive in 4th. These rules here are quite helpful because they're called the complementary angle rules, and essentially what they are is all centered around this pi on 2 property. Sometimes you'll see stuff with like 3 pi on 2 and stuff as well, but it's essentially just this, except plus a pi, and so you do this part first and then you can kind of move pi or do whatever you need to from there. But essentially, if you imagine kind of what we were talking about before, about the triangles and how the sine and the cos just flip based on where the angle is, which one is the adjacent, which one's the opposite, that's exactly what's happening here, right? So if we had an angle x here before, and now we're having pi minus x, it's going to be the angle up here, pi over 2 minus x. So it's just going to swap the angle. So we can kind of see those two make sense, right? Because within the triangle, it just switches where it sits. In terms of the pi on 2 plus x, it's, I guess, a little bit more complicated, because you can see that the cos goes to negative side instead. And that's essentially just because if you imagine where pi on 2 plus x would sit, it'd sit about here, right? So instead of your triangle being like this way, it would sit up there. And that's completely okay, but just remember that cos was going to be negative in this quadrant in the first place. So what that means is now, because cos was going to be negative in that quadrant, the sign that's going to be resulting from that is also going to be negative. So it's just something you have to keep in mind. And essentially, if you just imagine it's the same thing that they've done with the angle up here. So they've just essentially switched the focus of the angle, so that instead of you having x here, you're going to be thinking about this angle pi on 2 plus x. So the angle down here will be x. And then from there, you can kind of use that. If you were to minus pi on 2, get pi on 2 minus from that, you would get, once again, that pi on 2 minus x up there, and you'd be able to switch it over. So if you think of it as, it essentially is our pi on 2 minus our x, that angle here, so essentially here, pi on 2 minus x, so essentially the angle in here, and then you've plus that back in. You can kind of imagine that goes to here instead. And just the main thing to remember for this one is why this cos goes to negative sine was because cos was going to be negative in the 2nd quadrant, whereas second sine wasn't going to be negative in the 2nd quadrant in the first place. Cool. Alright, so let's evaluate a couple of these exact angles. So we can evaluate them either with the triangle, or we can evaluate them with the table. So let's do one with the triangle, one with the table. So we'll have a triangle here, it's 60 degrees, so I'm going to use this triangle here where I have 90 degrees here, I'm going to have 60 degrees here, and I'm going to have 30 degrees here. So this means that it's my equilateral triangle that's been chopped in half. So it's going to be 2 here, 1 here, and root 3 here. So what I get is it's going to be SACs, so opposite over hypotenuse. So I want my sine 60, so it's going to be this one here. So I want my opposite over my hypotenuse, which is going to be root 3 on root 3 on 2. So my sine 60 degrees is going to be equivalent to root 3 on 2. Alright, so tan negative 5 pi on 6. So because this isn't in our normal values, I guess it isn't in the first quadrant values, we can kind of re-evaluate. So in terms of negative 5 pi on 6, that's going to be, here isn't going to be negative pi because we're traveling pi in the opposite direction to the positive direction. So here's going to be negative pi. So what we're going to have is it's going to be not yet reaching that, and it's going to be here. So that's going to be negative 5 pi on 6, right? So if we get negative 5 pi on 6 here, what we're going to get is that it's going to be pi on 6 left over there. So that's the triangle that we're actually going to be working with. And we just have to figure out whether tan is positive or negative. And using our cast, we figure out that it's positive. So we can use that. So this we're going to say tan negative 5 pi on 6 is going to just be equivalent to tan pi on 6. And essentially, let's just use the same triangle rather than writing it out because it uses the same triangle. So tan pi on 6 is equivalent to tan 30 degrees. And because the kind of the transition between the two is that if you want to go from degrees to radians, which they sometimes do a little c, so let's say degrees, radians. So if you want to go to from degrees to radians, what you do is you divide by 180 and times by pi. If you want to go from radians to degrees, what you do is times by 180 and divide by pi. So essentially, if you just divide whatever the value is by 180, you'll get how many pi's you need. And for this one, so if we wanted to convert it, divide by pi, get 1 on 6 times 180 is 30 degrees. So we can look for tan 30 degrees, and tan 30 degrees, according to this, is going to be our opposite over our adjacent. So our 30 degrees is 1, right, over our adjacent, which is going to be root 3. So we're going to get that it's going to be 1 on root 3 or root 3 on 3. Coolios. Alright. So moving on to a bit more complicated angles now. So these are called the compound and double angle rules, and they're very important because they will come up now and then haunt you basically forever until the end of VCE Spec, because they are used a lot in circular functions, evidently. But they're also used a lot in other contexts as well, particularly with calculus questions. They're also used a lot for those. So I think it's really important that you get these down well. And because they're on the formula sheet, it means that you don't particularly have to memorize them. But I'm under the theory, or I support the theory that if you can be comfortable with these rules, it's probably better that you have some vague recollection of these rules rather than just solely relying on your formula sheet. And that's only just because of the reason that it will probably make you more efficient at doing questions. And it'll make you more efficient at doing questions, and I think it will also make it better in terms of recognition for questions which aren't so straightforward in terms of they tell you that it's going to use circular functions. So question like calculus questions. So if you can do that recognition, it's helpful to know what's going on, and it's more helpful that you can recognize what's going on so that you can do the question and recognize what rules you need to use. Cool. Alright, so we've got two questions here. We have cos 75 degrees and sine pi on 8. So cos 75 degrees is going to be equivalent to cos of 75 times pi on 180. So that's going to be equivalent to cos of 5 pi on 12, right? because essentially you're going to have 15 divided by both, and if you divide 15 into 180, it'll give you 12, and if you divide 15 into that, it'll give you 5 pi on 12. So that's the angle we're going to get here, right? That's the angle we want. And we want to think about this. So the key thing with finding exact angles which you don't have an exact value for straight away is you want to identify what this can be made up with, right? So 5 pi on 12, the pi on 12 things are probably the most common ones that come up with this, just because if you think of the angles we do know, it's pi on 2, pi on 3, pi on 4, and pi on 6. And if you think of the lowest common denominator for all of those, it's going to be pi on 12, right? So if we think about what we could do here, this would be 6 pi on 12, this would be 4 pi on 12, this would be 3 pi on 12, and this would be 2 pi on 12. So our goal is to form this. So our goal is to form 5 pi on 12. So we want to work out a combination of these which form 5 pi on 12. And the easiest combination we can probably see here is just plussing those two angles together, which makes our life very great in terms of just using those two angles. So what we can do is just use those two and we can put those in. So we're going to use pi on 4 and pi on 6 here. Let's rub dub. Okay, so what we can do is we can say this is going to be equivalent to cos pi on 4 plus pi on 6, right? So for how I remember cos and sine rules is the cos rules are always cos, sine, and the sine rules are cos, sine. So because the sine rule comes from sine will always take the first angle in the rule, so it'll always be sine, cos, right? So if this was a sine one, it would be sine pi on 4, cos pi on 6, and then plus cos pi on 4, sine pi on 6. So it's kind of, the sine takes the preference there. But for cos, the main thing to remember is because it's both cos, sine, the main thing to remember is which one is positive and which one is negative. And how I remember it is that cos, because it goes cos, it's always going to just be the opposite sign. So cos plus cos will just be minus in between, whereas if this was a minus, it will be a plus in between. For sine, it's going to be the exact same sign because it's going to just have sine cos plus sine cos or sine cos minus sine cos, depending on which one, depending on whether it was plus or minus in the first place. So it'll be the exact same sine. Sine goes to sine, right? So with the cos, what we'll have here is just cos pi on 4, cos pi on 6, minus sine pi on 4, sine pi on 6. So what we're going to get here is, if we think back to or we can do our table method here maybe. Let's do a really mini table. So whoop, 1, 2, 3, and we can just not include our other ones so that we can focus on these ones. So we can go pi on 6, pi on 4, pi on 3, and then this is sine and this is cos. So it was, our cos pi was root 1, root 2, root 3, and this was root 3, root 2, root 1, right? They're all over 2. Sorry, it's a bit hard to see. It's a bit tiny, I think. That's okay. All right, so cos pi on 4, we can see here cos pi on 4 is going to be root 2 on 2, and then cos pi on 6 is going to be here, which is root 3 on 2. And then here is going to be minus root 2 on 2 for sine, and then sine pi on 6 is root 1 on 2. So root 1 on 2, right? So we're going to get, this is going to be root 2 bracket root 1 minus root 3 minus root 1 over 2. So i.e. it's just going to be root 3 minus 1 times root 2 over 4, sorry, not over 2, over 4. And that's our final answer. So you can kind of see it doesn't look that gross, but it is definitely more gross than the actual angles we work on. Alright, So this one's a bit of a different one, and how I like to call this one is kind of doing like a half angle thing, because we know what sine pi on 4 is, and we also know what cos pi on 4 is. What I recommend, so that it doesn't get too mixed up, is just use cos pi on 4, because cos pi on 4 has a lot of really nice rules. As you can see here, there's a lot more rules for cos 2x than compared to sine 2x. There's a lot more variation in rules, and you'll see that your cos 2x is often more helpful. So I'm going to use cos pi on 4 here, and I'm going to say cos pi on 4 is going to be equivalent to cos 2 times my pi on 8. And what this will mean for us is that when we're going to put that in, right, we're going to put that into our cos pi on 8, 2 pi on 8, and what you're going to get here is that we can kind of equate that in. So we can do this and essentially say that this is going to be equivalent to our cos rule here, and we can just use one of these. If we wanted to find the sine one, we can use this sine one here. So it's going to be 1 minus 2 sine squared x, right? Or you could use, so you can use this cos 2 pi on 4, and then you can essentially use this one as your rule to put it in. So what we're going to get here is we're going to get this one, so it's going to be 1 minus 2 sine squared pi on 8 as our value, right? So then what we can do here is essentially we can just substitute our cos pi on 4 in, which we know is root 2 on 2, and we can just essentially solve like a quadratic equation from here. So we'll get that this is 1 minus root 2 on 2 will equal to 2 sine squared pi on 8. And what we can do here is just do that from there. So we'll get that this is going to be 2 minus root 2 on 4 will equal to sine squared pi on 8. So therefore sine pi on 8 will equal to plus or minus root 2 minus root 2 on 4, right? So let's go up to here because there's no more space. So it will be sine pi on 8 will be equivalent to, and what we can use here is that pi on 8 is going to be bigger than 0 and smaller than pi on 2. So therefore sine pi on 8 has to be bigger than 0 because it's in the first quadrant. So what we'll get here is that it will just be the positive version, and it will be root of 2 minus root 2 on 2. And we can kind of root the 4 so that it doesn't... Generally, people don't like surds in the denominator, so that's the only reason why. Cool. Amazing. And you can do the same thing for like cos pi on 8 or whatever. Let's move on to these ones. So these ones are essentially the trig identities. So you have the addition of angle rules, you have the double angle rules, and then you have these trig identities. So this trig identity should be quite familiar to you. This one also reasonably so. It's just derived from the Pythag theorem. If you think of the triangle that we form, this side is cos and this side is sine. So it kind of makes sense to why this cos squared plus sine squared. These two you can remember, but you don't necessarily have to remember because they just are derived from this one. So what you do is for this one here, what you're going to do is divide everything by cos. So if you divide everything by cos, what you're going to get here is sine squared over cos squared is going to just equal tan squared. Cos squared over cos squared is going to equal to 1, and 1 over cos squared is going to be sec squared. So that's where this one comes from. And for this one, what you do is you divide. So this is divided by cos, and this one is divided by sine. So if you divide everything by sine, you'll just get this. Sine over sine is 1. Cos squared over sine squared is going to be cot squared, and 1 over cos squared is going to just mean, 1 over sine squared is going to be cosec squared. So that's where this one comes from as well. So you can kind of see how the two rules were derived from those two aspects. Cot is just 1 over tan x. Sec is going to be 1 over cos x. And cosec is going to be 1 over sine x. So you ask me, why couldn't they have just made 1 over sine x equal to sec x and 1 over cos x equal to cosec x? Trig the the idea of trig is to confuse people, so that's why they did it. No, I'm joking. I'm not sure why it is, but you can just memorize that it's the opposite, because most things in trig are just kind of the opposite of what you think. Righty. So let's have a go at this question then. So they say sec x equals to negative 3 on 2, and x is bigger than pi and 2 smaller than pi, which means that it sits in this quadrant here. So they want us to find what sine x is, which means that we don't actually need to find what x is. We just need to find what sine x is, which is helpful. So what we can do here is we can identify that sec x is 1 over cos x. Sorry. 1 over cos x, which equals to negative 3 on 2. Sorry. Don't know why I just got a sneezing fit. 1 over cos x, which equals to negative 3 over 2. So we can kind of swap that over and say cos x will equal to negative 2 on 3. And then if we want to find sine x, we can just take it from the identities that we found before. So there's kind of two ways to do it actually. So there's one way you can do the triangles here, or you can find it via the identities. So we can try finding it via the identities. So cos x plus sine squared x is equivalent to 1. So if we plug that in, negative 2/3 squared plus sine squared x will equal to 1. So you'll get that this is going to be 4 on 9 plus sine squared x will equal to 9 on 9. So sine squared x will equal to 5 on 9, and sine x will equal to plus or minus root 5 on 9. So they've told us that x is bigger than pi on 2, smaller than pi, and we know, according to our CAST acronym, that sine is positive in that second quadrant and it sits in the second quadrant. So therefore you're going to get sine x will equal to root 5 on 3. Okie dokie. Alright. The other way to do it is you can use triangles. So you can essentially just do this and say this is your triangle, and you're going to just ignore the negative and positive, and we can work that out later. But you're going to say that your adjacent is 2 and your opposite is 3, and you can kind of work it out from there as well. So theta, so you're going to have 9 minus 4, and this is going to be root 5, and you can kind of see how you can work it out from there as well. Cool. Alright. For the function with the rule fx equals to 96 cos 3x sine 3x, find the value of a such that fx equals to a sine 6x. So this one might look a little bit complicated, and it's only worth 1 mark, but it's actually relatively straightforward. So all we need to do here is essentially recognize that this component is essentially just going to be the sine 2x rule. Right? And we know sine 2x is going to be equivalent to 2 sine x cos x. So we need 2 here, so what we're going to get here is going to be fx will equal to 48 times 2 cos 3x sine 3x. And we can just treat the 3x as if they were x, so all we need to do is double them. So what we'll get here is 48 times our sine 6x. So therefore, we're going to say that a is 48. Just like an important exam tip overall is that always look back to what the question is asking, because sometimes you put in the hard yards and you put in all the stuff and your working out is absolutely wonderful and you do everything that they need to. And this particularly applies to questions where there's like functions and they're like, oh yeah, so there's a, b, c, d, and then they get you to find the function, and you found your a, you found your b, you found your c, you found your d, you found all the pronumerals you find, and you just leave it, right? And you're like, yay, and you move on. But then what happens is you'll lose a mark because they ask you to find the function and you didn't actually write the function in the end, or you didn't write in function notation, or you wrote out this, right? You converted it into the form that they wanted it in, but you didn't find the value of a. So stuff like that are really important, and stuff that it's things to lose easy marks on, which you don't really want to do, because there will be things which are difficult and you don't know how to do, and if you lose marks on that, it's okay, because you didn't know how to do it and you'll find out how to do it for next time. But stuff like that is really hard to stop for next time, because, you know, it's a practice of what you're doing. So it's important to start building that exam technique really early on. Okie dokie. Alright, so let's talk a bit about the sine cosine rule now. So those were so there's kind of like two aspects to trig. There's the first aspect of trig, which is all about those angles, finding exact values, finding values and drawing out your sine, cos, tan graphs, doing all of that, the reciprocal graphs, all of that kind of stuff. And then there's like this side of trigonometry, which is more about geometry and talking about shapes and what's going on with shapes and stuff like that. So I would say the aspect which is more accessible is probably for next year. For this year, both of them are accessible, evidently, because both of them are part of the study design. But for next year, if you're thinking about in the future and the concepts which might carry over, the one that's going to carry over the most is probably the ones that we just talked about in terms of the angles, drawing them out, stuff like that, because it is very applicable for very applicable for calculus type topics as well. This topic, still a little bit in 3-4, but not as much. So what you'll see in 3-4 is they'll use this as assumed knowledge. So they'll use this as the assumed kind of geometry knowledge, because there's a lot of geometry involved in spec by nature, because there's vectors as a topic and all of that stuff involves shapes. So by nature, it is a topic which kind of gets assumed knowledge from geometry. So with these rules, even though they're not strictly in the 3-4 study design, what you want to know is just vaguely have these rules on your formula sheet and on your band reference. And what I recommend for this end of year exam as well is to have one list full of just all the geometry rules that you come across that are used. So stuff about parallelogram, stuff about squares, rectangles, triangles, circles, all that kind of stuff, and just have a general repertoire of those types of things, because even though they might not be assessed as like a sole thing by itself, they will definitely come up in the context of other questions where you could use another method to help you, but it's often easier just to use that method to do it, and you've already got a nice tidy rule to do whatever you need to do. Cool. Alright, so let's talk about the sine and cosine rule. So there are essentially three main rules that are about triangles, right? So all of the stuff we talked about so far was all in the context of having right angle triangles, and that was talking about our graphing, all of that type of thing, all of the finding exact angles, using our Python rules, lovely stuff. But there's also another side of kind of trig, which is all about the triangles which aren't the right angle triangles, right? So your isosceles triangles or your scaling triangles, or just your random equilateral triangles as well, that aren't anything that doesn't involve a right angle. Even if it does involve a right angle, these are still applicable, but I guess it kind of cares for the side which doesn't have that right angle thing in there. So what we're going to have here is the cosine rule is used when there's two sides and an included angle, or if three sides are given. And what it is it's going to be a squared plus b squared plus c squared minus 2bc cos a. So for example, for this one, if we're finding, the main thing to remember is that it's the side that you want that corresponds to the side of the angle, and the other things are just kind of inserted in between. So the main thing to remember here is that you have your a squared here, and you want that angle to correspond. So that's why it has to be an included angle. Alternatively, so if you have the three sides given, what you're going to find is the angle, and if you have two sides and an included angle, what you're going to find is the side. So what we have here is that we have our a squared, and then what you have is your b squared plus c squared. And you'll see when we talk a bit about vectors that this formula kind of looks a little bit similar to the vector formula as well, and they do have overlaps, and you can use the vector formula to help you prove this formula as well. Cool. So the sine rule it applies when we have one side and two angles given, so i.e. a kind of angle side angle situation, or if we have two sides and one non-included angle. And if we look at that triangle, so essentially the sine rule is based on so if you kind of cut this off, so it's normally either one or two. You normally don't have three things that you're finding at once. So if you think about what you're trying to find, right, you're going to have one unknown. So that means that you need to at least have one pair of stuff, and then you have one value for one of these. Because how the sine rule works is it's kind of like a ratio type rule. So the ratio of the side to its angle is going to be equivalent to the ratio of the side to the other angle as well. So that's how it kind of works. And what's most important is that you have at least one pair. If you don't have one pair, that's really problematic because you can't really do anything. So for example, if you had A sine C and then you had B and if your three pieces of information was A, B, and then sine C, you can't really do anything with that information in terms of the sine rule. You could do something in terms of the cos rule because you have A, B, and the C, but you can't really do anything in terms of the sine rule. So it's most important is that you recognize which rule to use, because like we saw before, it is possible to convert between sine and cos quite easily just using the Pythag rule that has sine and cos within it. Cool, let's go through some examples. So, if we have find A, B, and capital A, so we want A, B, and capital A. If we know B equals to 60 degrees, so we can kind of draw this out so we don't doodle all over the triangle in the corner. With these triangles, they can be any shape you want. They can be weird, they can be wonky, they can be really look like anything. And the whole point is try not to make your triangles look too nice, because if they look too nice, sometimes our brains get tricked into looking at the sides and we're like, ooh, those two sides look equivalent. And then for some reason our brain makes them equivalent. So it is actually better to make your triangles a little bit weird and wonky. So we're going to go A, B, C, and then we'll have C, A, B. So they want us to find A, B, and A, big A. So B is 60 degrees, C is 40 degrees, and little c is going to be 7. So they want us to find A, B, and stuff. So what we can see here is that we have one pair. So we have C and C here. And we have our B left over as well. So what that means to us is that this will enable us to actually find out what our B value is. So what we can do here is therefore we can find what our B value here is. So what we can get is that we'll get that this is going to be B, right? B over sine 60, i.e. sine capital B, is going to be equivalent to C, which is 7, over our sine C, which is sine 40. So we're going to get B is going to equal to 7 sine 60 over sine 40. And often these will tell you, however many decimal places. So what you can do is you can just plug it into your calculator. And the most important thing about the calculator used for these is you have to set your calculator either to radians or degrees. I would recommend to set it to radians because I think it's easier if you're in degree mode, it's really difficult to type things in radians. But if you're in, it's really difficult, and it's also you're a bit unsure because if you type something like 2 pi, it might take it as 2 pi degrees, so i.e. 3.14 degrees. So I find it easier to set my calculator in radians because if you want to write in degrees in your radians mode, all you have to do is put the degree sign there and it will automatically calculate as degrees. So what we can do here is we can go sine 60 degrees, right, times our 7 over our sine 40 degrees. And what that's going to give us is it's going to give us that b will equal to 9.43 dot dot dot. And normally it'll be to 1 or 2 decimal places. So let's go with 9.43. Okay, so then you ask me, okay, so we found our b. How are we going to find out a and a? Because they don't directly give us any information about a and a. But what we also know, another important piece of information that we know about triangles, is that all angles in a triangle will add up to 180. So if we look at this triangle, the angle that we're missing here is 80 degrees, right? Because we need to go 60 plus 40 and then 80 degrees here. And you can see how off scale the angles in this triangle are, but that's fine. So what we'll get here is that a over sine 80, and we can right away actually say that a is 80 degrees. So a over sine 80 is going to equal to, and I like to still use the same one I used before, so the sine 40, because it's always better to use information that you've already got rather than information that you found. So a will equal to 7 sine 80 over sine 40. So if we kind of plug that in, what we're going to get is, we can use the previous thing that we just did. We'll get that a will equal to 10.73 approximately. Cool. Amazing. Alright, so that's kind of an example of a sine one. And let's do a bit of rubber dub and talk about our cos one now. So we can go erasing gold slide. Alright, so find a if a equal to 6, b equal to 10, and c equals to 5. So now we can see that we've got 3 sides and we're trying to find one of these angles. So really they could have asked us to find any one of these angles, right? Because we've got all 3 sides. But they asked us to find a, which is perfectly fine. So we're going to go 6. So the rule is a squared equals to b squared plus c squared minus 2bc cos a. So that's what we're going to put it in. So we're going to have 6 squared equals to b squared, which was, I'm not sure whether b or a, no, b was 10. So 10 squared plus 5 squared minus 2, 10, 5 cos a. Okay, so then we can do a bit of rearranging and kind of switching around. So we'll get 36 will equal to 100 plus 25 minus 100 cos a. So we'll get, this is going to be negative, 89. Yeah, negative 89, because when you put that across it's going to be 11, and then 100 across is going to be negative 89. So, or alternatively, you could go into 36 minus 100, which would be 64, and then negative 64, and then negative 64 minus 25 would have been negative 89 as well. So that's going to equal to negative 100 cos a. So therefore your cos a will equal to 89 over 100. So a is going to be equivalent to, and then you can do a bit of a cos inverse type situation to find out your 89 over 100. And just remember, if you're in radian mode in this thing, you need to convert it back to degrees. So you just times it by 180 and divide by pi. And it will give us that a is going to be 27.13 degrees. And you can find the other sides as well from that. So you can find, you can do this side or that side, doesn't matter too much. So you could find b here as well. And what you would need to do is replace that, kind of switcheroo the sides a little bit so you can find it. Okay, so those are the first 2 rules. So there's 3 rules kind of in total in this topic. The last rule is still related to the area of the triangle, right? So essentially the area of the triangle is just going to be a half BC sine A. And it's going to be based on the principle of these sides as well, and probably derived from the other 2 rules in order to actually find the area. But you can kind of see how that would work out also. Cool. Alright, So let's go through this one example together again. So find the area if A equals to 55 degrees, C equals to 35 degrees. So 55, 35, and A equals to 7, right? So what we can do here is, what we want to do is find the area of these ones. And what we know is we need a half BC sine A. So that means that we need to know what these other two sides are going to be equivalent to before we can really do anything. So there's kind of an option here. We can either do, this one where so there's kind of two options here. We can either convert it so that we find what this side is, because we don't really need what side C is if we're using the side C angle, and we can do that because we can know what the B angle is as well, and we can convert that. Alternatively, we can also use this ratio to find out what these two are, and then just use the 55 degrees. I think the more trustworthy one, the one that requires less working out and less things going on, is probably going to be the one where we just use the angle, we find out what this angle B is and find those two sides, then we use C as our primary angle. So let's do that. So we've got that 180 minus 55 degrees minus 35 degrees is going to equal to our B value, essentially. So 55 plus 35 is going to be 90. So what we're actually going to get here is that B is going to equal to 90 degrees. So that kind of changes things, because that will mean that this side is going to be the, the base and the height. So we technically could use that as well. But we can actually use that idea to help us kind of check what we're looking at, right? Because we've identified that B value is actually going to be 90 degrees. So let's just find out what B is going to be then. So B over sine 90, so i.e. 1, is, I put in too many things, sorry, too many degree signs, is going to equal to 7 over sine 55 degrees. So what that means is B is going to equal to sine 90 over sine 55 degrees. So if we put that into our calculators, what we're going to get is so B will equal to 8.55, let's say 8.55, so round to 3 decimal places. And so what we can get here is, therefore, if we want to find this value, what we're going to get is that the area will equal to a half BC. So our BC in this case will be these two. So it will be 8.55 times 7 sine 35 degrees. And so we can put that in and just check what that is. So even though I've rounded it off on the page, I haven't rounded it off in my calculator. So it just means that my answer will be more exact, and it's important to make sure not to round off as you go. So even if you write it as something that's already been rounded off, it's important that you kind of leave it unrounded in your calculator to make sure you get the most exact value as possible. So you'll get that the area here is going to be 17.156 or 17.16 essentially, and you can kind of check that via if for example you found what C was here, which would have been, so if you found what C was, which would have been C equals to sine 35 degrees over 7 sine 55 degrees, which would have been sine, so 35 degrees So yeah, so you would have gone sine 35 degrees, and then you would have gone that equals to 4.9 something, right? And then we identify how this is a right angle triangle. So technically we could just use a half base times height for this, and the height is just C, so it's a half C times 7. because base height. So it would have just been a half times 4.9 times 7, which would have worked out to be 4.9 times 7 over 2. So yes, it would have also worked out to be 7.16, which we would have expected, right? So you can kind of see how it works both ways. Cool. Let's try our second example on this, and I'll just clear the page before we do that. Amazing. Cool. So find the area if A equals to 3, B equals to 6, C equals to 8, and you have that B equals to 35 degrees. So you probably could have found what this was based on those kind of angles already. You could have definitely found those based on what those angles were already, but they've kind of given us a little bit more information to help us, which is really good. Cool. So because they just want a half BC sine A, what we can do is it will just be a half BC, so those two, 3/8 sine A, so sine 35 degrees. And what you'll get here is we can just times that across, and it'll be a half, so our 3 times our 8 times our sine 35 degrees all over 2. So you'll get that this area is going to be 6.8829 ... or 6.88. Cool. Amazing. Alright,